Let's look at potential locations where there is chances of MISI, the marine ice sheet instabilities that we talked about. So there is Greenland with 3 locations: Jakobsen Isbrae, Petermann Humboldt here, and northeast Greenland ice stream. And all 3 are currently under attack. So basically that means that they are potential locations for marine ice sheet instabilities. And Greenland looks like real bad news because there is no place where, other than these few locations with a little bit of ice mass accumulation, pretty much everything is bad news, and it's accelerating. So that's not good. Plus Arctic ice melting and the potential impacts on the jet stream and the invasion of warm air from the subtropics to Greenland is actually adding to this uncertainty as well. In Antarctica, the mass loss is mostly from the Amundsen Sea embayment down here and the Antarctic Peninsula region and sectors in East Antarctica such as the Totten glacier with this glacier with a 3.9 meter sea level rise equivalent. So if you have a place that is facing marine ice sheet instability potential, and you have the ocean that's warming and winds are changing because of the uniqueness of the Antarctic warming relative to the rest of the world, then you are obviously getting into potentially what are called tipping points or points of no return and so on. Plus, we always have to remember that ice sheet losses are not easily recoverable on human lifetimes. They take a long time, as we will see from one of the past example. Little bit of good news. This is looking again at the 0 to 700 meter heat content anomaly from NOAA. There were years where the increase in the heat content had flattened out because of natural variability and the AFC coupled interactions that basically made it possible for the ocean to not take up heat actually showed up as flattened ice retreats, glacier retreats, and not really huge accumulations, but at least reduced losses, which is good news. So there are fast responses in terms of the potentially calving and discharge and flows, which actually could be useful, especially if we talked about the SLCP mitigations. If short-lived climate pollutants can be mitigated and we can quickly begin to flatten the curve, at least if not bending the curve, then there may still be potential to prevent some of the ice sheet instabilities and slow down the discharges and so on. Just to remind ourselves, sea level equivalent from various land ice sources, Antarctic ice sheet, almost 58 meters of sea level locked in. I hope it's clear. Evaporation supplies moisture to the atmosphere, which travels to the poles, as a lot of the evaporation happens in low latitudes, travels to the poles as snowfall. As we said, Antarctica and Greenland are literally deserts, so it takes a long time to build the glaciers. Antarctic glacier only started building about 34 million years ago or so. So you can imagine how long it has taken to reach this stage. So when that melts, that water is released back into the ocean, and it's equivalent of 58 meters. Greenland ice sheet, 7.5 meters, and glaciers and ice caps over the rest of the world have about 0.32 meter sea level equivalent. So this is not a joke, right? Rising relative sea levels have various impacts in general, and especially during storms, because with each centimeters of sea level rise, you are going to get further inland the storm surges and inundation. And if you're having rapid intensification of cyclones and expanding of the tropics to bring cyclones further north potentially and so on, then those are going to combine with the sea level rise and multiply the impacts, which is already actually seen in some of the hurricanes making landfall over the Gulf of Mexico and the eastern seaboard of the United States, okay, and the island states as well in the Caribbean and in the Pacific also. So what are the impacts? Increase permanent and temporary land inundation. So temporary inundations are very different. In fact, there are many ecological responses associated with such temporary inundations, but permanent inundation, salinification of groundwater and soil and so on, they are not good. So that's going to create more nuisance flooding and impeded drainage if the ground is soaked and saturated, for example. Change in shoreline dynamics, more conversion to open water, increased coastal erosion, more shifts in coastal habitat types, though natural defenses can disappear, increase in storm flood hazards, so increase in flood impacts and damages, increased saltwater intrusions and shifts in hydrodynamics that I already mentioned, marine waters inundating the groundwaters, which is really bad for agriculture. Less freshwater supply and water quality changes, so health impacts as well. In terms of societal impacts, you will have infrastructure and property damage or functional loss. 50% of the population lives now within 50 miles of the coast, and this is projected to increase continuously till 2050, where more and more people want to go closer to coasts. With sea level rise, cyclones, and flooding, extreme rain events, and so on, this is just not a good situation. Land use change or land or loss, environmental shifts and freshwater habitat loss, so inundation of saltwater, wetlands, etc. are going to have serious damages. Freshwater supply loss, public safety and health concerns, of course, inconvenience and economic disruption, investment costs of adjustment, protection, and restoration. Right now, in places like the Carolinas in the US, for example, asking people not to build close to the coast or even moving away from the coast is not easy. People are not going to accept that at all. Okay, so let's look at one example of past warming where sea levels were higher, and the warming range was pretty much what we are expecting in the 21st century if we don't bend the curve in a hurry, right? So this is showing here temperatures in Celsius as an anomaly with respect to a base period about 1960 to 1990 or so. So we had the so-called Eemian deglaciation, so the warmest temperatures of this record going from the present to about 150,000 years ago. So that's fairly recent, and that deglaciation was somewhat like today, where all the glaciers over North America and parts of southern hemisphere were gone. And then the ice age that ended about 20,000 years ago started. So here you can clearly see the asymmetry of the ice albedo feedback. This is coming out of the previous ice age, and the termination to here is very, very abrupt. Okay, you can see that it's happening in about 1,000 years with hiccups within that are of the order of a few years and a decade or two. Okay, so the ice albedo feedback in the warming phase or the glaciation termination phase is very abrupt. Building a glacier, on the other hand, happens in hiccups and takes a long time, because as cooling happens, because of the orbital changes, the ellipticity of the orbit changes on a 100,000 year time scale, the obliquity of the Earth's tilt to the orbit ecliptic plane of the ecliptic changes from 22.5 to 24.5 over 41,000 year time scale, and the precession of the equinoxes. The orbit itself keeps jumping around, is shifting of the equinoxes, for example. That happens on some 23,000 year time scale. So that triggers internal feedbacks, and if a cooling is triggered, what are called Melancholic cycles, very predictable changes in orbital forcing, then glaciers begin to build, reflection of the sunlight increases, temperatures drop further, but as temperature drops, atmosphere holds less moisture, so the snowfall rates over glaciers begin to drop. So building a glacier takes forever, but melting it, see, we came out of the last maximum around 21,000 years ago, very abruptly in termination 1, with a little hiccup here about 12,000 years ago that was happening at decadal time scale. Okay, so the system has these abilities to surprise us by doing things that can be very, very abrupt in the melting phase, and we are now in the melting phase because of global warming. Okay, so this is the sea level and the CO2 changes associated with the Eemian. At present, in the Eemian termination 125,000, 130,000 years ago, sea levels were 6 to 9 meters higher than the present levels. Okay, so the CO2s from 1890 of about 280 ppm before the Industrial Revolution have jumped to over 400 by now and increasing by about 4 ppm per year. And the warming since the pre-industrial period, we are just over 1 degree centigrade. And in the Eemian, the changes, the temperature anomalies were order 2 degrees to 3 and 4 degrees, depending on if you look at global mean or local warmings. So potentially that means if we don't bend the curve, we will be looking like the Eemian with 6 to 9 meter sea level increase. This is going to be a disaster for most of the island states, most of the low-lying areas like Bangladesh, Florida, Gulf states, and so on, and many other states, nations around the world. In the Eemian period, during the last interglacial, temperature at the surface of the Earth was only 0.5 degrees to 1 degree C warmer than present on average, but sea level was 6 to 9 meters higher. If the Earth's climate reaches a similar state, it's likely that sea level will rise multiple meters again. Okay, not at all good news. So keep the paleo analog in mind. What is possible in the climate system with the kind of warming we are looking at in this 21st century?